Yeah, so the last time we went through the construction of all the irreducible representations, which were for SU2 case was just labeled by one number, the spin j, which could be integer or half integer. Right? And then we also talked about the Casimir, right? And also the center of the group, how it acts. So there are two different classes. One where the omega, center of the group, was Z2, so identity and omega. Omega is -1 in this particular case. So omega -1, I mean, as a matrix, SU2 2x2 matrix. But when you look at the representation, we found that omega is +1 whenever j is integer, and it's -1 whenever j is half integer, right? So the set of all representations splits into two classes. These are usually called conjugacy classes. We will see this happens in all the other groups also. But SU2 was a simple example. Okay, now for the complex, so there is for any representation, you can also define a complex representation. For any, you can define a complex representation. Okay, so just to motivate this, I turned it on, I think. Yeah, turn it on. To motivate this, take the defining representation, or which is what is called fundamental representation. Defining fundamental representation. Well, those are just the two-dimensional representation. So those are the original sigma matrices themselves, right? So we had sigma A, I think we were using 1/2 or not. Yeah, so we were using 1/2 of the sigma matrices, but anyway, it doesn't matter. So sigma A by 2, sigma B by 2, commutator was simply I epsilon A B C, sigma C by 2. Now the claim is that if so let's just take the complex conjugate of this matrices. Okay. So the complex conjugate will be, so let's take, so let's take explicitly sigma 1 by 2, sigma 2 by 2, commutator is I, sigma 3 by 2, right? Because epsilon 1, 2, 3 is 1, and so on. You can write down all the different. Now let's take the complex conjugate of these matrices. So sigma 1 bar by 2, sigma 2 bar by 2, commutator, is going to be minus I sigma 3 bar by 2. Right? It's called minus because I, when you take the complex conjugation, is minus I. But this I can rewrite, this minus I can absorb in the following way. I define minus sigma 1 bar by 2, minus sigma bar 2 by 2. That's equal to I minus sigma 3 bar by 2. Okay. This minus didn't do anything, because minus times minus is plus, and all I've done is that minus, I put it inside the. So what we are seeing is that if I take this matrices, whatever the R of some Lie algebra generator, so this could be the first one, second one, or third one, whatever. If I let this R of X, R is this matrix now, right? This 2 by 2 matrix, in this particular case. If I take it to be Rx, or the complex conjugate of this matrix, then the algebra doesn't change. Algebra remains the same. You see, it's the same algebra. So if you just replace each of these guys by minus times the complex conjugate, then the algebra remains the same. So this is so that means that once you have constructed a representation, some matrix for the matrices for all the generators, then another representation comes for free, right? You don't have to do anything. Just take the complex conjugate of that, multiply by a minus. That will again satisfy the same algebra. So it's a representation again. Okay. Now, in general, I mean, these representations may not be different. I mean, in some cases it may be really inequivalent representations. So what do you mean by equivalent or inequivalent representations? Is that if there are two, I mean, you may have some way of writing the, say, some n by n representation matrix, and there could be another way of writing another n by n representation. But if there is some similarity transformation which takes you from one to the other, then you say it's an equivalent representation, right? Because after all, similarity transformation is a change of basis, right? You change a basis, and then, so in different, if you choose different bases, then the matrices will look very different, right? But they will still satisfy the same commutation relations. Okay. So if the two representations are related by similarity transformation, then you say they are the same. They are equivalent representations, right? Now in SU2 case, it's very simple. Why? Because I mean, after all, if I take a matrix of some spin J representation, so it's a 2J plus 1 dimensional, right? Matrices. Okay. Now you do this operation of the complex conjugation, you know, minus times the complex conjugate. It will give you again a 2J plus 1 dimensional representation, right? 2J plus 1 by 2J plus 1 matrix. So the representation has to be the same, because we saw that there is a unique spin J representation. You may just change the basis. That's all you do. Right? And in fact, you do change the basis, and that you can see by the following fact. Remember, we had the way we started the construction was going to the Cartan subalgebra, right? And then find the eigenfunctions of the Cartan subalgebra, right? So that is how we started, and then apply the creation and raising and lowering operators to construct the whole states, right? So if you look at the Cartan generator H itself, and in a given representation R, so the eigenvalues were so J minus 1 all the way up to minus J. These were the eigenvalues of the different states, right? So this was the highest weight state, then E minus acting on the highest, R E minus acting on the highest weight state, highest. This is a short form for highest weight, HW. And so on. You keep going down. Now, if I use this rule, the complex conjugate representation will be minus R bar H, right? But notice that in this basis, RH is of course real. It's diagonal and real. Actually, in this basis, RH was simply a diagonal matrix with entries J minus 1 all the way up to minus J, and everything else 0. All the off-diagonal terms 0. So it's clearly real. Huh? So complex conjugation doesn't do anything, but you get a minus sign. So this minus R bar H is the same as that, except the signs get flipped. Huh? So that means the eigenvalues have become, so so some state J, let me just label it like J. J is a total spin, and N is the particular number, particular state. N goes from plus J to minus J. Right? So what has happened is that since the signs flipped, essentially it went to J minus N. Right? But that is clearly just relabeling the basis. You have just chosen a different basis. So that immediately shows that it's the same, it's equivalent, right? Because it's just change of basis.
I can choose a basis in which this representation is complex, right? Each of the elements.
Yeah. I mean, you can choose any basis, but whatever it is, I mean, the statement is invariant. The statement that the representation is the same.
Okay, but it's not necessarily real, the representation.
It's not, yeah, it doesn't have to be real. Yeah, I mean,
okay.
Here I've chosen just such a basis where,
I see.
Because remember, H itself was Hermitian,
Yeah.
right? We just chose it to be sigma 3 by 2, right? So the eigenvalues of these guys are going to be
I see.
Yeah. Okay. So this was the statement. This is, of course, the peculiarity of SU2. We'll see that already in SU3 this is not the case. The complex conjugate representations are not necessarily the same as the original representation. Okay. We'll see that. I mean, when we discuss next week, we'll start seeing that. Okay. Now, the complex conjugate representations are useful to define some inner product, okay, which is invariant unto the group. Okay. That is discussed here in the next section. So, I mean, if I just look at now a fundamental representation. So, okay, once you have this here, I mean, at the level of generators, you have also the representation of the group G, right? Because G is nothing else but the exponential of the various generators, right? Various generators. So lambda, in this particular case, lambda A. So G is like I lambda A sigma A by 2. Right? So lambda A are some numbers, some real numbers. So the generic element of SU2 will be given by that. So what you will do is that you can, since I know how the sigma A, the representation will be given by R sigma A by 2, right? You just put that matrix in this exponential and that will give you R of G. R of G will be simply e to the I lambda A R sigma A. So that's you can of course then also define the complex conjugate representation R bar of G. That will be simply e to the I lambda A by 2, lambda A R bar. R bar, I mean, well, the complex conjugate representation is minus R bar G, right? So this will be minus R bar. I don't know, what shall I say? I mean, this complex, yeah. So in the so I will define this complex conjugate representation will be simply the complex conjugate representation of the generators and exponentiating that. Okay. So sigma A by 2. Right. So I think, okay, let me just use the same symbol, same notations. So this will be all 2 by 2 matrices, right? Because in this particular fundamental representation, this is simply R sigma A by 2 is the same as sigma A by 2. So let me just forget about that and just look at the fundamental representation. I will call it R fundamental. R fundamental. So sigma A by 2, here I will get minus sigma A bar by 2. Right? This will be R bar F. So given some, so this is going to act on some two-dimensional vector space, right? This fundamental representation is going to act on some two-dimensional vector space. So let me call the fundamental representation as phi, which will have two labels. I will use the same notation here. We will keep some indices lower and upper, but that's just for convenience. It's not so important. So this phi has some index I. Two indices. I goes from 1 to 2. Those are the two states. This will be 2 columns, so phi 1, phi 2. Right? 2 column vector because it's 2-dimensional representation. So you have phi 1, phi 2. And how does this transform under this object? So phi I will go to RF G. In the notes, one has omitted this. In the notes, we have just written this as some Gij. Okay. But it does. I'll just keep this thing to remember that is a fundamental representation. So in the notes, this is written as simply Gij, but it's understood that this is the fundamental representation. So the transformation will be this, goes to that. That is how it will transform. Right? You see, this is the phi 1, phi 2 are the matrix here. And here you just multiply, when you make this transformation, you just multiply by this matrix, RFG. And this is just the matrix multiplication. Now, let's look at phi bar, the complex conjugate representation. I will just denote it by phi bar I. This vector space, I will denote by phi bar I. Okay, this I just put the index up for convenience. Is not important. So you remember always that the lower index for the original representation, we use a lower index, and for the complex conjugate representation, we use the upper index. It's just a convention, it's nothing more than that. So how will that transform? That will transform as, so phi bar I will transform as, in the complex conjugate representation, which will be G bar, which I will denote by RF of G bar. This is a symbol, this is the complex conjugate representation, which is defined through that expression. RF G bar. And then I will use again, so here you have I, J, phi bar J. Because I'm using the upper index here. So this is still the this labels a, you see this index is before that index. So this is still the row and the column. So this is a standard matrix multiplication. Okay. Now let's consider this object, phi bar I, and some, okay. So some phi bar I, some psi j, psi I. So this is fundamental representation of, and this is some complex conjugate representation. So I guess they need not be the same fields. I mean, they could be something different, right? So some psi transforms as the original representation. Phi transforms phi bar, what I denote by phi bar, it is transforming under the complex conjugate representation. And I take the product like this. The statement is that this product is invariant under the group. Now, what is this thing? This is this I can think of as this is a column vector, and what I have to do is, I mean, I can write it in the matrix notation as phi bar transpose psi, right? I mean, think of this as a column vector, and that's a row vector, right? This sum I can write in the matrix notation as a product of the row vector times the column vector. So when I take the row vector, row vector is of course the transpose of the column vector. That's why I wrote this as a transpose. Right? Is that clear? So when I take the transpose of this equation, so transpose of this equation gives me phi bar, and then phi bar times the R dagger. Is a dagger representation. So in other words, this same expression, but now I have to take the transpose of this. So very explicitly I can write it. So if I take the transpose, I will just get I lambda and minus sigma A bar by 2. But then I have to take the transpose of this. Yeah. When I take the transpose, I will just get sigma A dagger. But sigma A dagger is sigma A. Okay. So that this part becomes e to the power of minus I lambda sigma A by 2. Lambda A sigma A by 2. So notice the phi bar this phi bar transpose goes to phi bar. Let me write it somewhere here. So phi bar transpose goes to phi bar transpose times e to the power of minus I lambda A sigma A by 2, whereas psi goes to e to the I lambda A sigma A by 2. Psi. So then it's clear that phi bar transpose psi goes to phi bar transpose psi, because these two things cancel. Right? So this was its original G, and this is G dagger. And G is it's unitary, right? SU2 group is unitary, so it cancels. So this is useful. It's very useful because after all, you say at the end of the day, what are we trying to do? So here we have studied all the representations and so on. But in physics, the way it appears is you have some action, classical action, right? Which is supposed to be invariant under the symmetry group, right? So these groups will act as some symmetry of the some action, right? So you may have some fields, I mean, we'll be talking about field theory in general. So some fields which will have some symmetries, right? Some SU2 symmetry. So those fields will transform in some representation of the SU2 group, right? Or any group. So and there will be lots of different fields in your theory, right? And each field will be transforming in different representations. Right? Now, ultimately what you want to construct is a Lagrangian or action which is invariant under the full symmetry group. Right? So then you may have a situation where there is a two-dimensional representation, fundamental representation of SU2, and you want to take another field which is also transforming under the fundamental representation of SU2, and you want to construct something which is invariant, right? To have a term in the action which is invariant under the group transformations. So this tells me that if I have a fundamental representation and if I have an complex conjugate or any representation and its complex conjugate representation, then I can just multiply them and that would be invariant. So this will be the this is our motivation. We want to construct actions which are invariant under the symmetry group. So this one gives you that already at the quadratic level. I mean, in general, okay, let me, maybe I'm saying too many things which are. So in general, in the fields theory, you can have various sets of fields. I don't know, let's say phi, choose some other name, psi, chi, lambda, all sorts of fields may be there in your theory. Each one of them may be transforming in different representations, right? Maybe this is transforming in some R1 representation, this is transforming as R2, R3, R4, whatever, right? All these different things may be there. Now what you want to do is to construct an action, which is of course, depends on all of this. Action will be a function of this. I mean, fields, of course, they are depending on x, right, their position. But I'm ignoring the x because I'm thinking of this group action as some internal symmetry, right? Although you can also talk about the symmetries which act on the space. But let's, for simplicity, take it to be just an internal action. So it has some indices, I, where I runs over the dimension of this representation, right? This may have some index A, which runs over the R2, dimension of the R2 representation, and so on, right? Now, what you want to do is to construct some kind of an action which involves all of these guys. I mean, for example, okay, there will be kinetic terms, but then there will be also the potential terms, right? Minus the potential energy term in the action. This potential energy, this function, will be a function of all these fields, phi, psi, chi, lambda, etc. No? But not an arbitrary term can appear here. Whatever combinations you choose, right? It better be invariant under the group. Otherwise, it will not be a symmetry of this action, right? So what we are seeing here is that already I can write down a quadratic terms in this. For example, phi, psi, quadratic term, right? Provided if this was a given representation, if phi has to be in the complex conjugate representation, then I can immediately write down invariant. Right? So this whole issue of constructing invariants, because that's what will appear in the action. But of course, also, I mean, you can have a cubic terms here, or quartic terms. All sorts of terms can be there, right? If there are only quadratic terms, this is what you call a free theory. Okay? But then you can have cubic terms, quartic terms, all sorts of terms, which will give you interactions, which will make the theory non-linear. Right? If it is just quadratic, it becomes linear, meaning equations of motion are linear. Right? Equations of motion are obtained by taking variation with respect to the fields. So if it's only quadratic terms, kinetic energy is quadratic, right? Then also potential energy is quadratic. Then when you take a variation with respect to any field, you're going to get linear equations. That's why I say it's a free theory. But once you have cubic and other interactions, you get interacting here, right?
So to construct such term, the representation should have the same dimension.
Yeah. Exactly. If you have for the quadratic terms to occur, which is invariant, these two must have the same dimension. Yeah. Not only the same dimension, but must be in the complex conjugate representations. For SU2, it doesn't matter, because in SU2 we saw that the representation is self-conjugate, self-complex conjugate, right? Any given representation is conjugate to itself, right? So SU2 it doesn't matter, but in SU3 it will matter. In SU3 the defining representation, which will be 3 by 3 matrices. So the fundamental representation is three-dimensional. But the complex conjugate representation is also three-dimensional, but it's not the same representation. Okay? It's really distinct. It's not, no similarity transformation can take you from one to the other. Okay? So in that case, in order to get something invariant, you must have both. Usually one writes it as notation is the three-dimensional representation and the complex conjugate representation, which we usually denote by 3 bar. Okay, this is notation, right? In SU3. Not in SU2, there is no problem. But in SU3, we will see. I'm just kind of jumping ahead, but I'm just saying that these two representations are distinct. They are not related by similarity transformation. Okay? So you need both of them to construct that quadratic term. In particular, to construct kinetic term itself, because kinetic term is quadratic, right? So if you want to write down any kinetic term for these guys, you better have also 3 bar. If you have a 3, you should have a 3 bar. That's what happens there. I mean, you must have all heard about quarks. Quarks transform as a triplet, right? But then there's anti-quarks which are 3 bar, which are transforming into 3 bar.
There's also color group, 3 color
group, yeah. SU3 color group, yeah. Okay, so this is some kind of, but also this now tells me that you should, I mean, we should have a way to construct invariants for the cubic and quartic terms, etc. Right? Otherwise, we will not have any interesting interacting quantum field theory, which has some symmetries, right? So that leads us to the next chapter, which is the tensor product representations. Okay? So because you see, so what? Yeah, or even for another application of the thing is the following. Now suppose I have some process where some particle, 2 particles come, interact, and a third particle comes out. Some process, you shoot 2 particles to each other, and somehow the third particle comes out. And let's suppose this particle is transforming in some representation of some symmetry group, some representation R1. This is transforming under some R2. Now, we are saying this theory symmetry, this group is a symmetry of the theory, right? So the interactions must preserve that symmetry. So what it means is that this guy, whatever it appears here, should be in some representation R3 in such a way that, let's see the following. This is the composite particle. I mean, these 2 things come together and it becomes a third particle. Okay. This state is transforming under a tensor product of R1, because this guy is transforming under R1 as a R1. This transforming as R2. So the total thing, the combined thing, will be a product representation, right? Because this, yeah. So you have a product of these 2 things. But here is again a single particle. Okay, is going to transform in some representation. So the statement is that. So what kind of particles can appear here? Not any particle can appear here. You see, this R3 must be something which is contained in the product of these 2 representations. So it's okay. Maybe it will become clear once I start talking about the tensor products. So first of all, let me just keep. I'll come back to this. But first, let me define what's tensor product. Because otherwise, this will not be very clear. Okay, so the tensor product representation of two are R1 times R2. So R1 times R2 is defined in the following way. Okay. So we have, say, some field phi which transforms under R1 and some field psi which transforms under R2. Okay. Now we want to define, so how will the group act? So, and I take the product of these 2 fields. So a group G, group element, a finite group element G, what it will do, it will transform both of them. So first of all, let me see, how many states are there now? I want to take the product. This has index I, and this has some index, let me call it A, because these indices range are not the same in general, right? So I goes from 1 up to dimension of R1, and A goes from 1 up to dimension of R2. Sorry, repeat that again.
Both of these equal.
Same group, same group. I'm looking at the same group. Of course, this may have transformed under some other groups also. Like that's what happens in standard model, right? Quarks will have a color group. It transforms under a color group, but it also transforms under a SU2 group. So a single object can be transforming under two different groups. Okay, but let's simplify the problem for the moment. For the moment, we're just focusing on one group, one particular group. So under that group, say this one transforms as R1 and this transforms in R2 representation. Okay. So the range of indices are this, right? So the total number of states here is dim R1 times dim R2. Right? Because this index can go from 1 to that, and this can independently go from 1 to that. So the total dimension of this field, the total possible field combination that we can take is dim R1 times dim R2. Okay, that's it. So so if I take one of these guys, how is it going to transform under the finite group element G? Some say G is in the so this is transforming under in some group G. So we are concentrating on some group. Okay. And let's suppose G is an element of capital G. Then clearly the phi will transform say as G phi I, R G phi, sorry, R1 G phi I. So phi I will go to that, right? So this is in the note. Okay, let me write like I J phi J. Okay. And the other hand side, A will transform to as R2 G A B side B. Okay. So this is what's going to happen. This phi I psi A will go to this combination R1 G I J phi J times R2 G A B side. Right? Here's the summation. J and B are summed over. So that's how it will go. But then you can ask the question: what is the infinitesimal version of it? This is a finite group element, right? Now, infinitesimal version, this would become. So now I look at the infinitesimal version. Infinitesimal version of the statement. Well, this one will go like this one will become identity of that dimension, identity matrix of dim G, dim R1 dimension, and plus a small thing, the Lie algebra element. This is what we call the Lie algebra representation of the Lie algebra element. Let's say, so think of G as some 1 plus X, identity plus X, and X is infinitesimal. So we ignore all the quadratic terms. We just ignore all that. So I'm just looking at the infinitesimal version of it. So this will become identity plus R1 of X. Okay. And then here Ij, Ej. And similarly here it will become, this will go over to identity plus R2 of X, and then AB side. So if I open it up and see what is the infinitesimal change, right? When I look at the infinitesimal change, so this when I open it up, first of all you'll get a term identity here, but that gives you back the same thing, right? It will just give you phi I psi B, psi A, right? So that is. But now what we're interested in is the change, how much it changes, right? The change is given by, and only up to the linear term, first order term. Not quadratic, second order term, first order term.
Can we add infinitesimal parameters in there?
Yeah, if you wish, maybe I can put here an epsilon here. Okay. So then it becomes more clear, because here I'm ignoring plus order epsilon square, but I'm ignoring that. So here is epsilon also, and here is epsilon.
So the parameters have to be the same?
Because the same element I am applying, right? I am applying the same element, G on both, right? So it will be the same. It is simultaneous action on both. And now again I look at So first of all, I will get the identity operator itself, this product, which does nothing. I mean, so this state gives, so if I expand it, open it up. So I open that up. So the first term is simply phi I psi A, okay, which is coming from this identity. Identity is simply delta j, and this is delta AB. So it gives you that. But our real main interest is in the order epsilon term. So you will get here R1 of ij, phi j, times psi A, right? Plus epsilon phi I RAB, R2AB, R2X, R1, R2X, AB, psi. So you see, so what has happened here is additive. At the level of Lie algebra, it is additive. So it acts, the Lie algebra element acts on one of them. At that time, it doesn't act on the second guy, right? Plus another term where the first guy, there's no action, just identity, right? And second guy is a Lie algebra element acts. So the action is additive. It's like taking derivative. When you take derivative, it will be what is it called? This law, right? What is it called? What is it? Product rule. Yeah, I mean it's Leibniz rule, right? Yeah, F1 F x G Gx. You take d by dx, so it will be the sum of two terms, right? Where first one acts here and nothing on G plus F times dg by dx. In a sense, I mean, the Lie algebra really, the action of the Lie algebra derivatives can be thought of as some kind of a derivative. Okay. So that is the way the Lie algebra acts on the product representations. See, the group acted simultaneously on both, the finite group element. You transform both of them by the same element in appropriate representation. But at the level of Lie algebra, it is clear that since we are looking at the infinitesimal version, order epsilon term, right? At order epsilon term, it becomes additive. It acts like a derivative. So, all right. So that is the way it transforms. Now, what I will do is that so in this chapter we have discussed the tensors and so on, right? But instead of that, I will come back to it maybe on Monday. But I will try to present it in a way which is a bit different from this. Then I'll come back to this on Monday. So okay, so let us look at this here. And ask the question. So the point is, the whole problem with this is that this representation that we have found is this one, dim R1 times dim R2, right? Because this guy has dim R1 possibilities for this index I, this has dim R2 possibilities of index A. So the total dimension of this space is dim R1 times dim R2. Point is that this is not irreducible. This may be irreducible. Suppose I have chosen this to be irreducible and that to be irreducible. Okay? But the product may not be irreducible. Okay? So what is important for us is to decompose this in terms of irreducible representations. Of course, this is going to be a representation of the group and therefore a Lie algebra, right? But the point is it's not a irreducible representation. Okay? And our aim is to decompose into irreducible representations. So what we want essentially from this is that R1 tensor product R2, okay, we want to rewrite them as sum over irreducible representations. This is our aim. And this is important because you see, as I was saying that example, so suppose I have a particle phi and a particle psi, so this one is transforming under R1 and R2. And out comes some particle here. Now this particle better be in one of these irreducible representations. Otherwise, it will not appear. Okay. Or vice versa. I mean, or equivalently, you can say, if I have such an interaction, then I must have a term in the action. So suppose something lambda is coming here, phi psi lambda in the action, right? Because that is how the phi times psi can give you a lambda. Okay, two particles come, and you have not done the field theory yet, but I mean, this kind of intuitively more or less clear, right? In field theory, it will become more clear precisely how that works out. But so if you have this, if this is R1, R2, what could be the possible representation here? Those representations will appear here. So that's why, if for physics, it's very important to decompose, to be able to decompose this. These tensor product representations into irreducible representations. So what I will try to do now is to just for the SU2, I will try to work out in a different way than that. We will come back to that, but I think what I'm going to describe here, it gives you the basic idea. What's the procedure? Of course, this basic idea, if you try to use it for very complicated representations, products or big representations, it becomes rather messy to deal with it. Or several products. Here I just took the product, two of them, right? But in general, you can have R1 times R2 times R3 times R4, etc., etc. Then it becomes very cumbersome to use this procedure. But this procedure will give you the basic concept. What is it that one is doing in this decomposition? This is the decomposition of the tensor product representations. Okay, so let's look at SU2 case. And let us in particular look at, this is for arbitrary x, but let us study what happens when x is equal to the h, the Cartan generator. Okay. So in that case, what's going to happen here is that you will get R1H acting on phi. I will not write this indices. I mean, it's clear that this index is a summation. Let's see. Psi plus you get here phi times R2H acting on psi. Okay. So this is what you get. Now, of course, I can choose a basis for the phi and psi, right? Which are already diagonal, which diagonalize the h, right? That is how we constructed all these representations. H was diagonal in that representation, right? So suppose this is spin j. In fact, in the 1 and 2, let me write it as spin j and spin j prime, because representations are labeled by spin, right? In the SU2 case. So if I take spin j here and spin j prime here, so this is j representation. So phi is in spin j representation, and psi is in spin, say, j prime representation. So now, what we are saying is that on the tensor product, the Lie algebra acts like that. So I call these here tensor product. That is the rule. I mean, the way the Lie algebra acts on this tensor product is defined as this. So this is acting on phi and psi, phi times psi. So let me take that here. This is a definition. That is how. I mean, this is the representation. What is the dimension of this representation? Dimension of the representation is same as dimension of this times dimension of that, right? So in this particular case, this will be 2j plus 1 times 2j prime plus 1. So it is this dimensional matrix, which means this many columns and this many rows. So it's a huge matrix, right? And now our aim is to decompose into irreducible representations. So let's choose the basis for which is already diagonal. Okay. So in this, this will be, let us say, so I call it Jm, and here this state is in J prime, M prime, Jm, and J prime, M prime. Okay. I take a particular M prime. I take a particular state. Notice that M goes from minus J to plus J, M prime goes from minus J prime to plus J prime. And when you consider all this M and M prime, you get that. Right? So this is the basis for the full space. Right? I mean, this guy, this RT is going to act on a column vector which has this many elements, right? And those are just parameterized by m and m prime. As m changes and m prime changes. So let's just pick one of them, which is labeled by m and m prime. What am I going to get here? This will be m, right? Times the phi and psi, j prime, m prime, and that will be m prime, because here RH is acting on that in the j prime representation, which will have eigenvalue. So phi j m, psi j prime, m prime. So this means the eigenvalues are adding up, edited. So this is again an eigenfunction, but it is of eigenvalue m plus m prime. J m psi j prime m prime. Yeah. So the eigenvalues is added. Now, how do we see that? So how can we? So let us try to consider. Let's take a simple case first, and otherwise it becomes a bit messy. Again, you know this. You know the rules. You know what happens. You have already studied in SU2 case. But again, maybe the way again different people have seen it in different ways. So I just want to put it in one way. So let's see. So first of all, let's again look at. You remember the way we constructed the irreducible representations was by looking at the highest weight, right? Once you have the highest weight, then the representation is fixed completely, right? So let us see what is the highest possible eigenvalue we can have. Right? It's clear this highest value of m can be only j, m prime can be j prime. So the highest value of this is j plus j prime. So certainly there is a state which is phi j and times psi j prime. Okay? And this has eigenvalue j plus j prime. This is the RTH eigenvalue. The eigenvalue of RT. I forgot to write that H. Now, okay. Now let us look at the states which have the j plus j prime minus 1 eigenvalue. In other words, if I apply R E minus, the lowering operator on the state, which will again be a sum of two terms. Because this Lie algebra acts as additively, two different terms. So there will be one term where E minus acts here and nothing there, and plus another term nothing acts here and E minus acts there, right? So it will be a combination of the two. So actually there are two states. You can see there are two possible states here: phi j minus 1 and psi j prime. That is one state. And another state is phi j and psi j prime minus 1. Right? Both of them, when you add that up, this m quantum numbers, you add it up, you get that. Right? So there are two independent states. These two are independent states. Fine. So on the other hand, in this irreducible representation, there is only one state which has its eigenvalue j plus j prime minus 1. So what we are saying is that one combination of these two states, some particular combination of these two states with some coefficients, will be the one which I will get by applying lowering operator on this state. Right? But what happens to the other state? Say this is two-dimensional, right? There are two states. One combination is what's coming here by applying the lowering operator. RT E minus. When I apply on this state lowering operator, I will just get one state, right? Definite state, which will be some definite combination of these two states. But then there is a linearly independent state left over, which has the same eigenvalue. Okay? That means from out of this combination, these two, one combination comes like here, but the other combination does not come from here. So the other combination itself is a highest weight state. It is a highest weight state, highest weight state. Okay. So then we find, so this highest weight state is something, I mean another combination. So it's a combination of, let's call it, I don't know, state 1 plus state 2. Right? So 1 plus 2. It's some combination of 1 and 2 with some coefficients here, which is linearly independent of that. And one can actually precisely see which particular combination, because if it is to be highest weight, that means E plus acting on that should annihilate it, right? By definition, highest weight state was something which was annihilated by the raising operator. So you can apply raising operator from on this combination. Well, when I apply raising operator here, let's say on this state, on that state, the state what I call state 1, again it will be additive, two terms will appear, but raising operator annihilates that, because this is already the highest weight. Raising operator will act here and give you back that, right? This also, when I apply raising operator, nothing happens here, right? It annihilates it. This one will go there, right? So both of them go to that, but with some definite coefficients.
There should be a minus sign there.
Well, it depends on the precise, how you normalize these things and so on and so forth, no? The precise coefficients. Yeah, if you just, not really, because, the way we defined in our original thing was that phi j minus 1 was simply R e minus, R1 e minus acting on phi j, right? But then when you apply R e plus on this, you will get this commutator term and you may get some number. No. It depends on how you normalize it. Whatever it is going to be some number times that. This is also going to give me some number times that. So you choose this combination that vanishes, which is always possible, right? This you can always do. So that's what I'm saying. So this particular combination is such that RE plus RT acting on E plus, and this is 0, on this state, on this combinational state, is equal to 0. Then that's the highest weight state. Right? So, and then you keep going. Now if you go to the next level, you have j plus j prime minus 2, then you see there are several possibilities. I can have phi, okay, let me suppress this in order to, because it's understood this spin j, that is spin j prime. I will just write the n quantum number. So this is j minus 2 psi j prime, one state. Then you have another state which is phi j minus 1 psi j prime minus 1, and another one phi j and psi j prime minus 2. Right? There are 3 states at this order, at this level. Now we already have obtained 2 representations. One is that original one, and another one which is that this is another highest weight state, right? So from here again I can apply lowering operator, and from here again I can apply lowering operator, right? So by applying lowering operator on this state, so meaning 2 lowering operators on that, you get 1 state, right? Applying 1 lowering operator in here, you get another state. But here we have 3 linearly independent states, right? So both of these guys, by applying the lowering operator here or there, is going to give me some combinations of them, right? But they will span, they will be linearly independent, right? Because they cannot be this proportional to each other. Well, otherwise, how can it be, right? Because here if I apply RE plus square, you get 0. Whereas here you apply RE plus square, you get that, right? So clearly these 2 states, here, so what I'm saying is that apply RE minus, you will get some combination of these 3 states, right? Apply 2 RE minus RE minuses, you will get another combination of these states. It won't be proportional, they will be linearly independent, because otherwise you would be in contradiction, right? So these 2 states span they span 2-dimensional space. Yeah. But then there is still a third one left over, right? Which, so you can find again a combination of them such that RE plus again annihilates it. So that means that then I have another highest weight, which starts at j plus j prime minus 2, which has spin j plus j prime minus 2, and so on, right? It keeps going. Okay. Of course, it could happen that at some point this becomes 0, because it depends on the value of j and j prime, right? For example, if I take, let's take an example. Let's take, suppose J and J prime both are J and equal to J prime equal to half. Then there's not much, right? Because the first one, the first highest weight was J plus J prime, which is 1. So J plus J prime is 1. And then the next one, we have J plus J prime minus 1, which is 0. And that's it. You cannot go beyond that, right? Because the J has to be non-negative, right? And indeed, you see that that's all, because there are 3 states here. Dimension of the spin 1 is 3, right? Plus 1, 0, minus 1, the m quantum numbers. Whereas this is spin 0, so it is just 1 state, singlet. Right? So there's 1 state here. Total number of states is 4, but that's exactly what you'll find, because this is dimension 2. I am taking the product of 2 dimension 2. So total dimension is 2 times 2, 4. So this is complete. That's no more states are left. This takes care of all the 4 states. Right? If you take, for example, if you take spin 1, suppose I take the product of spin 1 with this means spin. Huh? Not to write this. Yeah. So okay, J equal to 1 and say J prime equal to half. Suppose you do that. Okay. So the first we start with 1 plus 1 half. Okay. Then you get 1 plus 1 half minus 1. So this is 3 half, sorry, this is 3 half. The next one will be a spin half, because 3 half minus 1. And then it stops there. Cannot be, because if you subtract 1 more, you get a minus half. No? This is spin total J. So again, there are only 2 representations. And let's count again. So this is 4-dimensional representation. 2J plus 1, which is 4. And this is 2-dimensional representation. So we are saying it should be 4 plus 2. Right? And if you count it, this is 3-dimensional. That is 2-dimensional. Product is 3 times 2, 6. So this is the rule that you have, I think you all have seen, that spin J, product of spin J with spin J prime. So if I take the product of spin J with spin J prime, you get all the representations, you start from J plus J prime, sum, J plus J prime minus 1, all the way up to J minus J prime, modulus J minus J prime. Right? You have seen that. That just follows from here. Okay? So systematically, the underlying principle of this is systematically you start from the completely highest weight with nothing. There's no eigenvalue more than this in this representation. You first take out that representation, then look at the remaining states. Among the remaining states, again find what is the highest value of the m quantum number, right? Because then that's going to give me another highest weight, another representation. Remove all those states. Then look at the remaining ones, see what is the highest weight among the remaining ones. Highest quantum number of the H of the sigma 3. And then again that will give another representation. It goes on, and then finally you exhaust all the states by the time you reach there. So that's the procedure. This procedure we can apply to any Lie algebras, because in all of the Lie algebras, representations will be labeled by the highest weights. Okay, and weights are always adding. You see, because it's additive. I have a product of 2 representations. The weight of the product representation is the weight of the first representation, weights of the first representation plus the weights of the second representation. So it's all additive. So this will apply to every. Of course, it becomes very cumbersome. If it becomes large representations, then you want to consider many products of many representations. Then it becomes cumbersome to deal with it.
We know that there is some state which is not separable into 2.
Sorry, repeat that again.
We know that there are some states which are not separable into 2 distinct states. We call them entangled states. So can that kind of state be disappear?
No, that is a very different situation.
Those states will not.
No, that's a very different situation. Here I'm just talking about. That's a much more complicated.
Those states will not.
So we are not even considering those states. They simply just at the level of tensor product of two representations.
Any state can be separated into tensor product.
Not any state can be. I mean, here actually we want to go other way around, right? I mean, it's okay. Of course, you can go inverse also. We were thinking about this process, no? So here is R1 and R2. What kinds of states can appear here in a say scattering process or something where two particles come and joins and forms a third particle? Yeah.
So if I take any other state which appears there, can I decompose that into
Yeah. So the statement is that this whatever particle appears here must be in one of these representations. Otherwise, it cannot. This process will not go. Right? So suppose this was spin j and this spin j prime, and here is a part. I want to ask whether there's a particle can come which is spin j plus j prime plus 1. That's impossible, right? So this, yeah. It's just basically the kind of conservation, right? I mean, j, for example, h quantum numbers must be conserved, no? Because we are assuming that there is symmetry of the theory, no? So those will be conserved in any process. Of course, you can go other way around. Just change the arrow. No? So a particle comes and kind of splits into two particles. No? Then again, you can ask the question: if I have some representation R3 here, what possible things can appear? If this is R1, what has to be this? No, not arbitrary. You cannot have just arbitrary emissions. No, the symmetries restrict what kind of particles can come out. Okay. Any questions on this? I think you all know the result. This result you have all seen in quantum mechanics course, right? And probably you have derived also this way. I don't know. Yeah. No, you did. Yeah. Okay. Now the remaining time, maybe I can start. Let me see if there's something else to say here. Yeah, well, okay, one more comment you immediately see from this, that this was at the Lie algebra level, right? At the level of group, at the finite group element, what happens with the tensor product is that the group acts on this and this simultaneously, right? So this will transform as a G acting on that times G acting on that. So it's not additive, it's a finite group. And you see immediately that remember again, since we discussed about the center of the group. Center of the group is 1 and omega for SU2. If I apply omega on this tensor product, it will be the omega acting on that times omega acting on that. Right? So it will be the product of the two. So you can see again that we saw already that omega, whenever it acted on half integer spins, it gave you minus. And whenever it acted on the integer spins, it gave plus. So suppose suppose both of them are half integer spins. Then omega will give you minus here and minus there. So product is plus. So that immediately tells you that whatever you get on the right hand side better be integer spins. Which of course you will find, because if both are half integer, j plus j prime etc. will be integer. Right? And so if you take this one of them to be half integer, other to be integer, then you will get minus. Because minus times plus. No? Will be minus, and that is indeed the case. If one of is half integer, other is integer, then everything which appears here is half integer. So it's all consistent with the center.
So we have shown that if we have an odd number of fermions, we will get a negative sign.
Yeah, correct. Yeah. Right. Yeah, but of course this one, this is just fermions was just an example. I mean, I tried to give, when we said that when you rotate by 2 pi, you don't come back to it, so you get a minus sign. No? But you can even think about it, forget about the fermions, or take out just a boson, which is transforming in some SU2, but SU2 is the internal group, not the rotation group. Not the rotational group, but some internal group. In which case you can choose a doublet which is perfectly boson. But it's internal group, it's not the space.
It's not a thing in space.
yeah, is not the rotation. So yeah, in fact you will see that in the standard model, which is the model of, which is the most successful, I mean, it has explained, it has been really quite remarkable actually, standard model, you know, because yeah, it is the simplest possible groups, you know, you can think of. You have U1 is the simplest one, of course. The next one is SU2, and the next one is SU3. So and these are the groups which appear there, quite amazing. Product is direct product. Sorry, repeat that again, I couldn't hear.
The product U1, SU2, SU3 is a triple product.
Yeah, it's a direct product, yeah, not a semi-direct
It
product.
doesn't come from one group. So there are three parameters. One parameter of each.
I mean, okay, we can think of it as one group, but that one group is a product of these three groups, U1, SU2, and SU3. They're a direct product, which means the SU2 elements will commute with SU3 elements. They don't have a non-trivial commutation relation.
Can we do it in non-trivial?
Generators. Yeah, generators will have a commute. I mean, I don't know, you have, okay, we didn't discuss semi-direct product, but you already know semi-direct product in the, have you done Poincare symmetry? Poincare algebra? So in the Poincare algebra, there are two things. One is a Lorentz transformation group, right? Other is a translations. If you take translation by itself, it's an abelian group, right? Because it doesn't matter whether you translate first in the x direction, then in the y direction, or vice versa, result is the same, no? I mean, the Lorentz group is not abelian. It's a what you call SO3,1. But then you take the Poincare group is a product of these two groups, but that is not a direct product because the translations don't commute with the Lorentz group, right? Because what happens? So if I first do the translation, a point has gone to some other point, right? Given by this translation. Then I rotate. Then that point is going to rotate under Lorentz group, I mean Lorentz transformation, it will go there. On the other hand, if you first rotate by Lorentz transformation and then translate, it's going to be different because when you first translate and then rotate, then that translation vector also gets rotated, right? Whereas in the second way of doing it, the translation vector is not getting rotated. So it is not, it's not a direct product, no? Because Lorentz group acts on the translation vector also. So it's a semi-direct product. This is what is called semi-direct product. But that's not the case. For SU3 cross SU2 cross U1, we are talking about direct product. All the generators of these groups commute. Okay, so there is there are this, you can define these tensors. You have already seen again, I think in you did special relativity. So you have seen, for example, since we talked about Lorentz group. So under Lorentz group, say so some x mu, for example, the coordinates x mu will transform to the Lorentz group transformation, right? Mu nu x mu. You have seen this. Have you seen this? Yeah. Okay. So that's fine. But what about? You can also ask about the tensors. No? Suppose I have some t mu nu, a tensor, a second rank tensor. An example is the eta mu nu you have seen, right? Eta mu nu is a metric. Right? Eta mu nu is a second rank tensor. So in general, this is an example. But in general, a tensor, the definition is this transforms lambda mu, say sigma, lambda nu, say alpha, t sigma alpha. Right? This is the way it transforms. So you see what is happening is that each index, on each index you have a Lorentz group acting on it. No? This is exactly like what we said, the tensor product. So when we take the tensor product, so the only difference between the discussion we made there and here is that both the index are in the same representation. They transform again exactly the same way, right? So this is like taking R times R. representation. Okay? Whereas there we were considering more general, R1 times R2, which need not be the same representation. But now when we talk about the tensor, all of these indices are in the same footing. No? They transform exactly in the same way. So here's this R times R. And indeed you can see that, so in this particular representation, this one is the defining representation. So this is 4-dimensional representation in the Lorentz group case, right? So this is 4-dimensional. Now here, these indices, each of them can go from 0 to 3, 0 to 3. So there are 4 possibilities, so 4 times 4, 16, right? So this tensor in general will have 16 components. And then the transformation is like this. Okay. So this is a special case of what we discussed before. Yeah? Okay. So now, you see, I mean, if you go through this here, in section 7.2, it is kind of, okay, I don't know. So section 7.2 is, so what we said is that this one is, so in general, let's say, I mean, now think of general. This was a particular group, Lorentz group, but in general there will be, say, some group G, and I have some representation R, which is some of dim R, dimensional R, I mean R with dimensional R. Then states in that, let's say phi I, let's say, I goes from 1 up to dim G, dim R, sorry, not dim G, dim R. Okay. And the various group elements will act as, so phi goes to phi I under the action of some element G will be given by R, G, Ij, phi J. Okay. In that representation. Okay. Now we can define the tensors again. So that corresponds to taking tensor product to the same representation R. Same, not different representation, same representation R. So I can talk about a tensor, say Tij or Ti1, I2, any number, Ik, let's say. Okay. So this is what is called the kth rank tensor. Okay. This guy is called second rank tensor. So the rank is just a number of indices. So this is called second rank tensor. So this is the kth rank tensor. Kth rank tensor, K rank tensor. So you can have all such representation. This is nothing else but what we previously, it's just R times R, where you take K number of them. That's the same. And how will this transform? This will transform as Rg, I1, J1, let's say, Rg, I2, J2, etc. Rg, Ik, J3 times the original tensor. So this will go to, under the transformation, this will go to J1 up to J2. That's a transformation. Now, I mean, you see, this kind of procedure that we were doing was rather cumbersome, right? You need to know all the weights, right? All the weights, and then you start removing the highest weight. Although conceptually this is what happens, this is what we are doing actually in decomposing, but in practice it becomes very cumbersome, right? So this whole technique, which is developed using this tensor, is that what one shows is that basically this splitting into reducible representation can be reduced to the permutation groups. You know, the various permutation groups by applying on the permutation groups on these indices. So there are the K indices, right? So there's a permutation group pk acting on that, right? I don't know what is the standard symbol for it. When I say pk, I mean permutation group of k elements, which has factorial k elements. So by applying this permutation group elements, you can separate them into irreducible representations. Okay. That is that becomes more kind of easier to deal with, and from there comes all this Young tableau. There are some techniques where you use Young tableau to find very quickly instead of going through that long procedure. No? So that is what the aim of that is. So to see this, let us look at, let's just take a second rank tensor. Okay. So I take the second rank tensor, T I1 and 2. Let's consider this here. So this has, and in fact, let's further simplify that we are talking about this representation R to be the fundamental representation. So take this to be the fundamental representation. Not any representation, but just take the fundamental. So in the SU2 case, if G is SU2, this will be a two-dimensional representation, right? So each of these indices will go 1 and 2, 1 and 2. But more generally, let's consider more generally at this stage. You see, let me just say, the section 7.2, if you have that I will not go through it. It's just you should study that section 7.2. The aim of the section 7.2 is the following. Okay, it is just to rewrite. I mean, this way of writing that so this becomes, how does it transform under the, say, the Lie algebra, so which means infinitesimal version. This will transform into say X under some Lie algebra element X, Rx, I1, J1, T, J1, I2, plus Rx, I2, say J2, T, I1, J2, right? Now it looks a bit. I mean, this is whatever the dimension of this representation is. So let's say I goes from 1 up to the dim of the representation. Then you see this is a dim R by dim R matrix. This is a dim R by dim R matrix, right? But how do you see? I mean, after all, here I know the number of possible. This is a dim R square dimensional representation, because this goes from 1 to dim R. This goes from 1 to dim R. So if you look at, put down all these possible components, this is dim R square. Okay, so it looks a bit strange. I mean, you would expect that I should be able to write this transformation as some matrix acting on, if you arrange all of these T's, so T11, T12, all of these possibilities. So this will be dim R square column vector, right? Then I should write the Lie algebra element as a dim R square by dim R square matrix. But here it doesn't look like, right? You're writing. So the whole purpose of that 7.2 was to just show that this is equivalent to writing this, this dim R square. So please just go through it. It is just to, it's not, there's not much there, but just to show that, you can write it like this. Okay. So how does this transformation look like? So we said this is a transformation, right? Now let's see. Already, can we say something about can we identify some invariant subspaces? So the total number of components we said is dim R square. Dim R square components are there. But can I find some subspaces here which are invariant under the action of the Lie algebra elements? Because if so, because remember, if it is reducible representation, then I should be able to see some invariant subspaces, right? So can we just see some invariant subspaces? So one thing you immediately see is that if I take symmetrize these indices, I1 and I2, instead of writing this, why not I just write J? Otherwise you have to put the subscripts 1 and 2 also. So Tij, right? And take symmetrized. So I will define symmetric and antisymmetric. So symmetric is by definition Tij plus Tji. Maybe, okay, I don't know if we use normalization half. I mean, that's not important for this. Okay, we write half here. And this is half Tij minus Tji. So this is the symmetric part of this thing, and this is the antisymmetric. That's the antisymmetric part originally. Now the claim, what we will show here is that if I start from something like this, which is symmetric part, the symmetric part will never mix with the antisymmetric part, and vice versa. So that means this is already invariant subspace. These two are already invariant subspaces. And that you can see from here. So if let us apply the, so first of all, that is what it is, right? So we have R acting on Tij, the Tij goes to, when I apply X, it gives you Rx, I say K, Tk, J plus Rx, J, K, J, I, T, K, K, no, sorry, I, K. That's what we get. So this is under the action of X. What about Tji? Well, that gives you again Rx, say Jk, Tki plus Rx, Ik, Tjk. Okay. Now let's just add or subtract these two things, right? Because adding that gives you that combination, subtracting gives you this combination, right? So let's just add or subtract. So if I take Tij plus or minus Tji, I will get, so just we combine the two things. So you get here Rx, Ik, Tkj from here, and from here you get plus or minus. So I'm taking this line and plus minus that, right? So if I just take these two elements, these two together, you get Tkj plus minus Tjk plus Rx Jk, which gives you Tik plus minus this one is Tki. So you see, the plus sign mixes only with the plus, and minus sign mixes only with minus. So already we have these two invariant subspaces, symmetric, and that's what happens in the case of let's take the example of SU2. In SU2, I take the SU2 and take this this representation R to be the fundamental representation. So spin half representation. So what do we get here? Each of them can go from 1 and 2. So 2 times 2, 4 components are there. The symmetric components, symmetric part will have 3 components. An antisymmetric part will have just 1 component, right? Because there are only these values. This can only take 1 and 2. So if I look at this here. So in this particular case, this becomes very simple because Tij symmetrized actually has what possibilities? You can have T11. So this contains T11, T22, and half T12 plus T21. Right? If you just plug that in here. Whereas here, the only component here, antisymmetric, is T12 minus T21. Nothing else. So there's only one. And this is exactly what you saw. So this is, remember, this is a tensor product of spin half with spin half in this case, right? Spin half with spin half gave you a spin 1 and a spin 0. And the spin 1 has 3 components, three states, and these are the 3. And spin 0 is just 1, that's that. In fact, in SU2 case, it becomes very simple. I mean, every time you antisymmetrize any second, in this case, this is in SU2 case. This simply antisymmetric part is going to be epsilon ij times something, times, let's say, I don't know, give some name, T, let's say. Yeah? Because each of this index can only go 1 or 2, right? So the only one combination is 1, 2 minus 2, 1, which is exactly epsilon ij. So it's going to be proportional to epsilon ij. And so this here, it is quite, SU2 case is quite trivial actually somehow. Okay. So this is a basic procedure. I must stop again. This starts getting a bit more complicated once the second rank, right? Now if you take, say for example 3, it starts becoming complicated if it's more than second rank. Because permutation group is more complicated, right? Here the permutation group was just exchanging the two indices, right? With the 3 you have more complicated. Right? Yeah, I mean that with the 2 index permutation group was just Z2, right? If you have just two indices exchange, if you again do the exchange, you come back to itself. So that is Z2 group. That is very simple. But three-dimensional permutation group is very complicated. It had, I think we discussed it as an example in the beginning. It had exchanges, but also a cyclic motion. So it turns out that there are several combinations you can construct. It was here. Yeah. So you can take, so I have 3 indices. So one possibility is to take a totally symmetric in all the indices. They're totally symmetric. The other possibility is totally antisymmetric. So this is totally antisymmetric. Of course, for this to exist, this range of indices must be at least 1 to 3, up to 3, right? Otherwise, this will be automatically 0. So in the SU2 case, with the fundamental representation, this is not there. But you can think of other groups or even take other representations of SU2. No? So at least you should have 3 different values for each of these indices. Otherwise, this will be 0. But in general, there will be this. And then, so in general, one can write, decompose Tij, a totally symmetric part, totally antisymmetric part, and then these combinations, which are written as Ijk with a semicolon here, plus Tikj, where these things are defined. If you see in page 42, these things are, so Tijk is totally symmetric. So you can write it as 1/6, and I will just write it in terms of the permutation group elements. So G12 plus G13 plus G23. So basically, I just take all the permutations, and the cyclic one G123 plus G132. You see, these are all the permutation group elements, right? The permutation of 3 things has 6 elements, factorial 3, which is 6, right? And this identity, this is the 1-2 exchange. So what this means is that exchange the labels in the first 2 position. This means exchange the label of between first and third position, 2, 3. What we discussed in the permutation group example, the same notation. So this acting on Tijk. Okay, and similarly everything else is given. So Tijk, totally antisymmetric, is the same, except you give a minus sign here, and minus sign here. So plus goes to minus here, just for these 3 elements. Okay, not for those. So you know that in these things there is always a kind of a Z2 grading. In the permutation group, there's a Z2 grading. You can give a sign to a single exchange of a pair, one pair. Take one pair of indices and exchange. Now there are also other elements in the group, which is where you do 2 exchanges, right? So those have even grading. I mean, so plus grading, and the ones which have odd number of exchanges, those have minus signs. No? So this here. So you remember this was obtained as a product of, say, I don't remember which one, this with that or something like that, right? Product of 2 of these exchanges gave you that, and this one was product of 2 other exchanges. So while you can make this minus, that is remains plus for here, to get totally antisymmetric combination. This is just a way of writing. I mean, we have these combinations, and what does it correspond to in terms of the permutation group? So this is a way of writing. Other two are more complicated. Other two are this specs. Yeah. So other thing is with this one Tij k is equal to 1/3 1 minus G13 times 1 plus G12 Tij. So this is acting. So this one doesn't do anything. G12 exchanges these two. Then, so for example, what does it mean? This means already when I apply here, I will get here Tijk plus T, exchange the first and two positions. So Jik, right? Then I apply that. So when I apply that now, one gives you nothing. One gives you back the same. So Tijk plus Tjik. But now on each of them I apply G13, right? So when G13 acts here, the first and third labels get exchanged. So you get here minus Tk Ji, and here you get exchange. Then you get Tk Ij, and then there is a 1/3 here. These numbers are not that important. These numbers are not, because essentially these numbers are fixed by saying that you just plug in this formula here, this one, and that one, and similar expression is, let me also write down Tikj is just 1/3 again, 1 minus G12 times 1 plus G13. So these numbers are fixed by saying that when you add all of them, you explicitly write down all of this combination which appear here, and then you will see that everything else cancels and you just get back Tijk. Okay? So though that is flexible, those coefficients, but it's not that important. I mean, it is just that this particular combination, this number is not important so much for this particular, for this purposes, for our purposes. Okay, so this is rather complicated, right? Because it doesn't. You see, if you look at this combination, it doesn't have any particular symmetry anti-symmetry property, right? Except you see that it is anti-symmetry. Maybe I made a mistake here. Minus G13. No, this is wrong, right? What did I say? Tijk. No, this is wrong, right? This is so first and third. So it's K Ji. This is wrong. I don't know if I made a mistake here. This is what exchange with the first and third.
That happens because of the one that multiplied with the second.
No, this was just that. Sorry, this I wrote that. Okay, Ji. Okay, correct. And then I applied on this guy. Okay.
So it's symmetric in the first two indices.
It's symmetric in the first two index. Yeah. But otherwise, okay. But okay, it will be, you can. Is there an exercise here? I mean, it's not an exercise here, but you can try to prove that these are indeed invariant. Under the group action, under the V algebra action, this combination will never mix with the other combinations, all of them. They're invariant subspaces. Okay, unfortunately, I have to again rush today. Yeah, it's actually quite late. I have to leave now because I have to go to the town to pick up my daughter at the school. Her school finishes now, so just